Let's do problem number 35 on page 212. And it says, here it is right here. It says a sled of mass m is given a kick on a frozen pond. The kick imparts to it an initial speed of 2 meters per second. The coefficient of kinetic friction between the sled and ice is 0.1. Use energy considerations. You have to use energy to find the distance the sled moves before it stops. So here, written it out. Here's our sled. Here's the ice. There's a coefficient of friction of 0.1. Starts off with an initial velocity of 2 meters per second. It's going to slide to a stop. We want to know how far did it go while it was sliding to a stop. All right, so let's do it. And it says to use energy. Well, here we've got a non-conservative force. I'm going to classify this problem. Is there friction? Is there applied force? Well, one of the mistakes students make is that it gave it a push. But that push is no longer pushing during the course of this problem, right? It's sliding to a stop. It's after you gave it a push and it's left your hand, and now it's sliding to a stop. So there is a force of friction. So I would start with this. The work done by a non-conservative force equals the change in mechanical energy of the system. And this is the work done by friction. So I'll go ahead and draw a little, here's my sled. I'll just draw it as a little box like that. And of course we've got the weight, we've got the normal force, and we have this force of friction. We want to know how much work was done by that friction force to stop this thing. Well, you have to figure it out from here. So the work done by the force of friction is the magnitude of the force of friction times the displacement, right? And that's what I'm trying to find. And times the cosine of the angle, which is 180 degrees. That's right, because the displacement is this way, but the force of friction is the other way. So that's where I get that -1. And that's going to be equal to the change in mechanical energy. Now, that's going to be 1/2 mv final squared minus 1/2 mv initial squared. I'm sorry, it kind of ran into that. Okay? So that's a change in mechanical energy. There's no potential energy in this problem. You know, so I look and say, where's the mechanical energy at the beginning? It's all kinetic energy. And of course, the final velocity is 0. Now we need an expression for the force of friction. Force of friction equals mu times the normal force. And I could be really formal about it and sum the forces in the y direction, set it equal to 0, and show that the normal force is just equal to the weight. But at this point, we've been doing this a long time, and I think you can say, oh, look at the free body diagram. Oh, okay, the normal force is just supporting the weight. So now I've got an expression here where I can go mu mg, that's the friction force, times delta x, and then we'll make this -1, cosine -1, equals 1/2 the mass times the initial velocity squared. Oh, there's a negative there, right? Minus. Oh, look, the negative cancels the negative. That's pretty sweet. Then, look, the mass cancels out. And whenever they do it, when they don't give you the mass, you can almost always bet that the mass is going to cancel out somewhere. So just go with it. Don't panic. So now I can solve for delta x. Delta x is going to be equal to 1/2 the initial velocity squared divided by mu times G. That's kind of awkward way to write it, but okay. And that's going to be, well, what is V naught? 2 meters per second. So it's going to be 1 over 2. V naught squared is, well, that's 2.0 meters per second squared. And then what is mu? Mu is given to be 0.1. What is G? G is 9.8 meters per second squared. And so that's going to be, let's see, that's 4 divided by 2 divided by 0.1 divided by 9.8 equals, and so delta x is equal to 2.04 meters. Let's check that. We have meters, second squared cancels the second squared. Meters cancels with the meters squared, leaving meters left over, so my units work. My units work, I probably did it right. There we go. So let's zoom out and take a look at the whole thing. So, they wanted you to use energy methods. There is another way. You could just do this using kinematics, right? You could use kinematic equation, but it said in the problem to use energy methods. So you need to do that. So you need to not only get to the right answer, but you need to do it the right way. Also, several of you, did you get the remind, right, that we're going to have a homework quiz? Now, I don't know what you're doing, but on your equation list, you can, if you know the problems, you can put down all these derived equations on your equation list. But that's, I don't want you to start with derived equations. I want you to start from basic principles and then work your way towards a solution. I think some of you started with this expression. Well, I want to know where that expression came from. Maybe some of you have a spectacular memory. And if you do, maybe you can memorize thousands of derived equations to solve these problems, but I'm thinking not. Also, on the AP test, even if you have thousands of derived expressions memorized, you're not going to get full credit for just starting here and plugging the numbers in and getting the answer in one step. You need to show that you know how to start from basic principles and get to the right answer. So please do that. It says use energy methods. Well, if you start from here, you're not really using energy methods. Maybe you did it in your homework and you wrote this down, but that's not going to get you full credit. Okay, any questions? Yes?
What do we need to do to correct this and get half credit?
Yeah, I'll tell you about that in a second. Any questions on this problem? Okay, that is all.